just check it if it works well or not. Okay, seems nice.
Yeah, so if it's okay for you, you can start. So 20 minutes of presentations, and then we will ask you some questions.
Okay, so I will start. So hello everyone, it's very glad to be selected as one of the finalists for the GT2L 2025 thesis prize. I'm Yue Sue, now I'm a maîtrise de conférence at l'IUD Université de Lille, and I joined the KISTAD in here Inox team for my research. And today I will present my thesis, heuristic and exact algorithms for solving the electric autonomous diorite problem. And before starting, I would like to talk something about myself. So before my position at Université de Lille, I have conducted a one-year postdoc at Cermix, École de Heuristic, where we have been working on the interaction between machine learning and combinatorial optimization. And we studied the application in revenue management. And I collaborate with Axel Parmentier and Antoine Désir. And before my postdoc, I defended my thesis in 2023 on July at Santa Sibelec, and my thesis is under supervision of Jacob Puschinger. And during my thesis, we have been working on the heuristic and exact algorithms to solve the EADARP, the electric autonomous diorite problem. And also, we have collaboration with Professor Sophie Pahak on multi-objective optimization. So my presentation is based on 3 works from my thesis, where 2 of them have already been published in journal Transportation Part B and eJour, and the last work from my thesis will be soon submitted to a journal. And now let's start with the presentation today. So what is the EADARP, the electric autonomous diorite problem? The electric autonomous diorite problem, it consists in scheduling a fleet of electric autonomous vehicles to provide ride-sharing services to a set of customer requests that specify their origin and destinations. So as you can see here in this example, it contains 2 electric autonomous vehicles here. And there are 4 kinds of different node sets in the EADARP. First is a set of original depots, O1 and O2, where vehicle must start their trips at. And the second is a set of destination depots, where vehicle must end their trips at. And the third node set is a set of customer nodes, where each customer request is a pair of pickup node and corresponding drop-off node. And the last one is the recharging station. When vehicle is running out of energy, it must visit the recharging station to prevent this situation. And in the EADARP, we consider there are several problem-specific features. We consider the first problem-specific features is that we minimize the weighted sum objective function, which includes the minimization of total travel time for all the vehicles and the minimization of total access user ride time for all the users. And the total access user ride time for a given customer is calculated as the difference between the actual user ride time and the direct travel time. So to explain this point, I give you an example here. So here below is a partial path that travels from the original depot O1 and passes through 4 customer nodes, and which includes 2 customer requests, request 1 and request 2. And here, upon each arc, I present the travel time on each arc. And here, upon this dashed lines that linked 1 plus to 1 minus, this is the direct travel time for if the vehicle travels directly from the pickup node 1 plus to the drop-off node 1 minus, and is equal to 16. And here, under each node, I also give the time window associated. And with those information, I have proposed a feasible schedule, which is made up by the service start time at each node along this partial path. And with this feasible schedule, we can calculate the access user ride time for request 1 and request 2. So associated that, assuming that each request is only associated with 1 customer, let's say customer 1 and customer 2, then the access user ride time for customer 1 is calculated as a difference between its actual user ride time, which is equal to 17 in this case, and the direct travel time, which is equal to 16. So the access user ride time for customer 1 is equal to 10. And similarly, we can calculate the access user write time for customer 2, which is equal to 5. As we only have 2 customers in these cases, so the total access user write time with this schedule is equal to 15. However, this schedule is not the optimal schedule that gives the minimal access user write time for this partial pass. Instead, we can delay the service start time at the node 2 plus from 110 to 115 so that the access user write time for request 2 is decreased from 5 to 0. And this arises the first challenge of solving the EADARP, that is how to optimize the access user write time. However, the most advanced state-of-art methods cannot minimize it exactly in the context of the EADARP. And the second problem-specific feature is that we consider the electric autonomous vehicles and we allow the vehicle to perform partial recharging at recharging station. It introduces a trade-off between the battery feasibility and the access user write time optimality. Because imagine that a vehicle recharged for a long time at a recharging station, it will definitely extend its driving range. However, the long recharging time may impact the scheduling part for the succeeding node, which may impact the access user write time optimality. And this arises the second challenge of solving the EADARP, that is how to handle the partial recharging. However, partial recharging has not been tackled exactly in the context of the dial-ride problem with electric vehicles. And here is a summary for the theoretical contributions that my thesis have made. So first, in the first stage, we have designed effective heuristics to solve the EADARP in an effective way. That is a deterministic annealing algorithm. In the deterministic annealing algorithm, we have introduced a fragment-based representation of paths to optimize access user write time in an exact way. And second, we have proposed an exact and efficient route evaluation scheme for a generated EADARP route. And then we have considered to develop an exact algorithm to solve the EADARP optimally. And we have developed a column generation algorithm where we have constructed a new graph, GSP, that captures all the access user write time optimal schedules. And this new graph is proven to be able to preserve all the feasible routes of the original graph. And on this new graph, we have applied a customized labeling algorithm where we tackle the partial recharging exactly. And now I will precise the contribution of each part. So let's talk about the deterministic annealing algorithm. So in the design of effective heuristic to solve the EADARP, there are 2 main difficulties. The first difficulty is how to do the cost computation for a given route, because we need to compute the minimal access user write time. However, in the literature, there is no method that can handle it. And the second difficulty is how to do the feasibility check in case of a neighborhood solution contains recharging station, because we need to consider the partial recharging as a trade-off between the battery and time window constraints. Both of those issues complicate the route evaluation process in the generation of the EADARP neighborhood solution. And to handle these difficulties, we have proposed different methods. So we have first introduced a fragment-based representation of paths, which allows us to compute exactly the minimal access user write time for a given route. And we have proposed an exact feasibility check process where the partial recharging is tackled exactly. And the combination of those 2 methods is an exact route evaluation process. And it is of linear time complexity after a very fast preprocessing work. And now I will present our fragment-based representation. So a fragment is defined as a sequence of pickup and drop-off nodes, where the vehicle starts empty as the first node and leaves empty as the last node. And for the intermediate nodes, there are passengers on board. So for example, here for this EADARP route, it contains 2 fragments, F1 and F2. And with this fragment-based representation, we have the following proposition. Each EADARP route can be regarded as a concatenation of fragments, recharging station in case of visited, origin and destination depots. And the access user write time is well defined on each fragment because when vehicle arrives and leaves the fragments, there is no open request on board. And here is the first main result of our thesis, is that we have proved for a feasible EAW routes, its minimal access user write time can be calculated as a sum of the minimal access user write time on the fragments that these routes have visited. So for example, for this route, its minimal access user write time is the sum of the minimal access user write time on F1 and the minimal access user write time on F2. And with these main results, we come to the idea that we can do a fragment enumeration process before running our DA algorithm. In the fragment enumeration, we enumerate all the possible fragments and we calculate the corresponding minimal access user write time for those fragments. And then in the DA algorithm, when we generate a neighborhood solution, we just do a sample sum because we just need to curate the pre-calculated results and then we do a sample sum. Then we have the exact minimal access user write time for this route. And this have a big advantage because it will avoid the recomputations in the heuristic and it leads to a linear time cost computation. And also here, I summarize the enumeration time for the instance to enumerate all the fragments. For instances with up to 15 requests, the enumeration time to have all the fragments and its corresponding minimal access user write time is less than 0.5 seconds on average. And for larger instances with up to 96 requests, the enumeration time is less than 10 seconds on average. And after enumerating all the fragments in the DA algorithm, we just do a simple sum, and the computational time for the cost can be ignored, actually. And with this method, we have obtained very nice results. Compared to the best reported results in the literature, we have provided 25 new best solutions and 45 eco solutions. And on newly developed larger scale instances, we provide 19 new best solutions, which may serve as the benchmark results for future studies. And now I will present the contribution related to the branch and price. So the core part for the branch and price algorithm is that we apply the column generation at each node on the branch and bound tree. And the core part for the column generation is to solve the pricing subproblems of the EAW to find columns with negative reduced cost. And the reduced cost is formulated in equation 3. And the first term of the reduced cost is the weighted sum objective, which contains the minimal access user write time. And usually, labeling algorithm is applied to find such columns with negative reduced cost. However, in the design of an efficient labeling algorithm, there are several difficulties. The first difficulty is how to calculate reduced cost during the label extension, because in the labeling algorithm, the partial path is not fixed until the sync node is reached. It's a dynamic process. So for the partial path with open request, we cannot calculate the reduced cost because the minimal access user write time is not well defined. So the first question is how to calculate the reduced cost. And the second question is how to handle the extension of path, because during the extension, if we only consider one optimal schedule of minimal access user write time for current partial path, then it may be impacted during the extension. And the third question is how to handle the partial recharging. In case of we extend the partial path to a recharging station, we need to determine how much energy to be recharged at the recharging station. As the partial recharging at the recharging station may have impact on the access user write time optimal schedule. And those are the three questions to be handled. And for the question 1, we have give our solution. So we take advantage of the fragment-based representation that we have introduced in our last work. And with this fragment-based representation, instead of extending the partial path node by node, we extend the partial path fragment by fragments. And in this way, we can calculate the minimal access user write time on each fragment exactly, and the access user write time is well defined and can be optimized. And second question, how to handle the extension of passes. So the solution is that we have proposed to abstract each fragment to an arc that captures all the optimal schedules. And this is the second main result of my thesis. So by extending the partial path fragment by fragment and capture each fragment to an arc that captures all the optimal schedules, we can capture all the optimal schedules during our extension. And the third question, how to handle the partial recharging. We have proposed to construct a new graph, GSP, that preserves all the feasible routes of the original graph. And on this new graph, each arc is ensured to be access user item optimal. And then we handle the partial recharging on this new graph without having any impact on the access user item optimality. And on this new graph, we apply the labeling algorithm based on the literature, where the partial recharging is handled exactly in the label extension. And based on those methods, we have obtained very nice results. So for our column generation algorithm, as a root node, we already solved 15 out of 18 instances optimally without branching. And we have found 22 new best solutions and 49 eco solutions. And we have improved 24 lower bounds and obtained 14 eco lower bounds. And the average gap is only 0.31% between the lower bound we obtained and the best known upper bounds in the literature. And by adding the cutting plans, we provide 29 tighter lower bounds and 49 equal lower bounds. And we have solved 16.6 out of 18 instances optimally and found 25 new best solutions. And by completing the branching process, we have finally solved 71 optimal 71 instances out of 18 optimally, and we have found 26 new best solutions, and we have improved 13 lower bounds and have obtained 15 equal lower bounds. And also, we have obtained some managerial insights in the experiments. We have analyzed the impact of integrating total access user item into the objective. We make the comparison of the solutions that we obtained by solving a single objective with the solutions that we obtained by integrating the total access user item into the objective. And we found that by integrating the total access user item into the objective, we have a huge decrease on the total access user item, but only a slight increase on the total travel time. And this gives a practical implication for the ride-sharing service provider, because it means that it's possible for them to largely improve the service quality while keeping the operational cost at nearly optimal level. And also, we have analyzed the impact of allowing unlimited visit to recharging station, and it helps to improve the solution feasibility and quality. And one of the important byproduct from our work is that our labeling algorithm can be used as an exact scheduling procedure to give access user item optimal schedule for an EAW route. And now I will present the contribution of our last work, the bi-objective EAW. In this work, we have treated the two objectives separately. The first objective is to minimize the total travel time, and the second objective is to minimize the total access user ride time. And the main goal of our research is to find the efficient solution and the complete Pareto front. And we have considered representative methods in the literature, such as the methods based on objective space search algorithm, for example, Epsilon constraint methods, and also the methods based on decision space search, that is the generalized branch and bound. And we have proposed a hybrid algorithm that combines the decision space search algorithm with the objective search space search algorithm. And we have obtained very nice results as well. But the things that I want to discuss with you is the efficient solutions that we obtained and the managerial insights. So here in the figure at left-hand side is the non-dominated points for this instance. And the x-axis represents the first objective, the total travel time, while the y-axis represents the second objective, the total access user ride time. And on the table at right-hand side is the coordination of each non-dominated points. The first column is a value of the total travel time, while the second column is a value of the total access user ride time. And actually, we found the points that located in the red square are very interesting for the profitable companies such as Uber, because you can see those 2 points here, they have a very low level in terms of the total travel time. However, their total access user ride time differs a lot. And this means that those companies can largely improve their service quality without degrading a lot their operational cost. And second, we found that those 2 points located in the blue box are very interested for non-profitable associations such as the Red Cross, because those non-dominated points, they have a very good level in terms of the access user right time. However, their total travel time differs a lot. And this means that those associations can reduce their operational cost without degrading their service quality. And now I will give a short conclusion of my talk. So in the process of solving the deterministic optimization problem, we have designed an effective heuristic methods where we have introduced a fragment-based representation of paths and an exact route evaluation scheme in linear time. And in the process of designing an effective labeling algorithm, we have proposed to abstract each fragment to an arc that captures all the optimal schedules. And we have constructed a new graph, and a customized labeling algorithm is applied on this new graph to solve the pricing subproblems. And we prove the effectiveness of our methods via extensive experiments, and we have also obtained some managerial insights. And in the process of solving the bi-objective EADARP, we propose to hybridize between the generalized branch and price and objective space search method, and we also obtained some managerial insights from the obtained efficient solutions. And that's all for my presentation. Thank you for your attention. If you have any questions, don't hesitate.
Thank you very much for this very nice presentation. We do have questions. Eric, would you like to start with your questions?
Okay, thank you for the very nice talk. Well, I've got a very simple question. What is the use of considering autonomous vehicles in your model? Because it does not seem to provide any additional constraint.
Yeah, it produce some additional constraints, produce some, let's say, specific features, I will say. So for example, let's look at this example. So by considering autonomous vehicles, it means that the vehicle can provide non-stop services. It means that when vehicle arrives at the destination depot, then it can start the service as soon as possible, because it's just to receive the request from the central command center and to process to continue the service. And this means that the original depot and destination depot in our case is not predefined, because in the classical DARP, the original depot and the destination depot, they are predefined. But in our case, we will not predefine the destination depots, because the autonomous vehicle can start their service directly, and it's actually a decision variable in our model. And I think this is the main constraints. And also, by considering autonomous vehicle, because there is no driver on board, so there is no maximal route duration constraints anymore in the model. Because in the classical DARP, there is a maximal route duration, because we consider that the driver cannot work 24 hours a day. So there is a constraint, and now we don't have these constraints.
Okay, thanks. I've got a small second question about the instances. Could you say more about the realistic side of these the instances you tested your methods on?
Okay, so I have prepared a slide to explain the instances. So we have considered 3 types of instances. The type A instances are adapted from the literature, and it's actually based on the classical DARP instances with adding the characteristics of the electric vehicles. And the second instances is also based on literature, but it's based on the real-world ride-sharing data of Uber technology. And it contains the largest instances in the second type contains 5 vehicles and 15 requests. And in order to test the performance of our proposed heuristic, we have built a larger scale instances which contains with up to 96 requests, 8 vehicle and 96 requests. So those are the informations for the instances that we have considered in our work.
The number of vehicles is not very large.
Yes, because actually the problem is already very hard to be solved. If we consider like 100 vehicles, I think it's very, very hard to be solved to obtain a feasible solution, I will say. And also one challenge of our work is that actually in the constraints, we have considered different levels of the minimal battery level that the vehicle must maintain when returned to the destination depots. So we have considered actually 3 different levels of minimal battery level. So the first level we have considered is 10%. So it means that the vehicle must return to the destination depot with 10% of the energy minimal. And the second level we have considered is 40%. And the last level is the hardest level, is the hardest one, which we consider that the vehicle must maintain 17% of the energy when it returns to the destination depots. And by considering those constraints, we already find it's very challenging to be solved. Even with the easiest case, with 10%, is already very challenging to be solved.
Okay, thank you.
Thank you so much.
Thank you, Eric. I have 2 small questions. You minimize the sum of total excess user ride time, and this may not be very fair because maybe there is a single user who has the total excess ride time. Would it be possible to extend your model to integrate some equity between the users?
Actually, the total access user ride time here, we consider the access user ride time for all the users.
Yes.
So yeah, for all the users. So I think this is already a criterion to reflect the user satisfaction, because with a lower level of access user ride time, it means that the users probably they are satisfied with the current planning because they don't spend a lot of time on board from sharing their ride with others.
Yeah, yes, but my question was, what if there is only one user who has a large excess ride time and all others have no excess ride time at all? This is not fair. And can you try to have some equity between the excess of ride time?
Yes, this may be interesting to discuss. We didn't consider this perspective in our current work. But in case of just one customer have a very large access user ride time, I think this is a case that cannot be be balanced, I will say. For example, if this customer, for example, it is he or she is delivered like directly from its pickup to the drop off, and they still have a very large access user ride time. It's just the saying that maybe the vehicle it arrives very, very early as a customer pickup node and a customer drop-off node, and this customer is waiting a lot of time as a drop-off node. I think it's a case that we cannot avoid. We cannot balance, and maybe this point can be discussed in the next step in the future work, because we are now considering dynamic EADAR case where the request is in real time. So maybe in this work, we can discuss more about, for example, if a user has a very large access user item, how to handle it. So maybe introduce some criterion to restrict these cases from happening. This might be interesting.
Okay, I have a very small question, very quick question. You have developed some code. Is it available as open source?
This is not available yet, because in our third work, we are still using the labeling algorithm to solve the bi-objective case. But after the submission of our paper, we will make it open source on GitHub. This is for sure.
Okay. Okay, thank you. Does anybody has any question? I think we have quite finished with the time of questions, but there is one very small question. It's okay. Otherwise, we can thank you again for your presentation. We will give you some news